So what happened was that I looked at my concrete distributions of the various weights at a fixed number of bricks. Then, assuming this to be something that looked like a normal distribution, then I asked Mabel to compute the variance, and then we looked at the variance as a function of the number of bricks and saw a systematic connection that looked a bit like a parabola. So now let's try to do this a little bit more systematically. What I did was I chose a log-log scale, getting a straight line, which says that there's a power law involved. But I can do this more systematically. I do a plot of the values between L and M being 200 and 250. So to get rid of the noise in the beginning here, I only look at the large numbers, and I can do a plot. And when I do a plot like this, then I get a very good fit, as you can see if I plot them together. Right? So the observations and the plot seems to go along very nicely, and I could take my fit to the transformed values and make it back into the fit of the actual values, and these numbers come out. I mean, the number that I had up here, which was the slope of the line, comes out as a power of 3, and then this number here is the exponential, I think, of this number here. But the point is that the power of x that I'm getting is a number that looks an awfully lot like 3. So it's tempting to make the assertion that, in fact, the variance grows like x to the cube, where x is the number of bricks in the original setting. So, I mean, that means that when I looked at this thing before we transformed it and thought I saw a parabola, I was wrong, right? Because this is not a parabola, this is more like a cube. So maybe now that we sort of know that, I guess I could see it too. But so that's the point of, doing these fits, of course, will help you stay honest in these kinds of observations. Okay, so now what is it that we have? So we've actually found something which is quite impressive, in the sense that for any fixed number of bricks, we have a good explanation or theory about what the distribution of the various weights will be, because we're expecting it to be a normal distribution, and we know the average of the normal distribution because by symmetry that has to be 0, and we also have a guess of what the variance is. So we have this expression that you just plug in the standard normal distribution, and we could try to compare that with our observations. And if we try to do that, you can see I'm sort of running into problems with this being a three-dimensional plot. So why is it a three-dimensional plot? Well, that's because we have two variables in play. One is the number of bricks that we're looking at, and the other one is the weight. So I have the bricks here only from 1 to 7 in this dimension here, and I have the weights distributed on the other axis there. And so when I plot this with my matrix plot, I get, of course, a 3D thing that Mabel put some colors on to help the eye understand that this is a 3D, supposed to be a 3D picture, even though, of course, it's a 2D rendition on a flat computer screen. Now, when I compare this to my hypothesis of a continuous approximation of this, then it's very difficult to sort of tell these two things apart, because you can sort of see that there's a plot of something continuous as well as these discrete observations. I can help the eye perhaps a little bit by choosing some colors. I don't know, this looks dramatic, I kind of like it, but I don't know if that's the best way of doing it. But what you can see is that now I took my continuous expression and made a red-ish plot of that, and I kept the other observations in black. And then what you can see is that this looks like the continuous expression is a very good approximation of the discrete approximation, in the sense that it's a bit like, snow that's falling on this sculpture here, that it sort of comes close to the big end and falls off at the small end. So I mean, I think this is a fairly convincing visual argument that what we have is a good approximation. And then, so what you can say, I mean, the best fit that I found for not only the number of towers that are maximally stable, but actually from the number of towers with any given weight is given by this expression, which is just I've taken my fit information and put it into the standard description of the normal distribution, and this is the thing that I've plotted in red, and you can see it fits very well the observations. So in a sense, this was a bit of a detour because I wasn't really interested in buildings with arbitrary weights. I was interested in the case where the weight was 0, but then that's already something, right? Because if I plug this into my expression and I just let W equals 0 in this expression, I get this thing out, right? So that actually tells us that the two observations that, I mean, or maybe they were more like guesses, that I was expecting the power of the number of buildings in that were maximally stable to be like 1 over x times x times square root of x. I mean, that's x to the minus 1/2. And I was expecting the variance to grow like n to the third. And that's actually the same hypothesis because there's a square root that comes into the expression of the normal distribution like this. So what we've seen is that by sort of expanding the view of our experiment a little bit and looking at more information which we already have, we can sometimes, by focusing on that, we can actually sometimes get information about the things that we were originally interested in. So this happens a lot in experimental mathematics, but for now, let's just think about what we did in terms of visualization. So what you could see I did a lot of the time was that I had some observations that were not linear, but I could transform them into something linear. So all the cases I did, I used the logarithm. So I had a doubly logarithmic plot and semi-logarithmic plots. But the point is that after I did the transformation, I could then find a line. I mean, the human eye quickly sees this is a line. You can find that line and you can transform back, and that gives you fairly good approximations of the data you have. And I made sure to be rather careful about not losing information in the transformations, right? Because what's going to happen in many cases is that if you take your data and you transform it, you may, because you're using logarithms or other dramatic functions like this, you will get rid of important information, and then when you do the best plot of that and transform back, you can see it doesn't fit at all. But here, the re-transformed information really seems to align very well with what I got out of fitting the transformed information, so that seems fairly solid. And of course, that tells me that if I'm going to try to make some proofs about these numbers considered by Watson, I should probably think in terms of probability and think in terms of some sort of distribution that fits the information here. And actually, you can do that. So it's you can find an expression for these numbers that converges in what's called distribution. So it's sort of a weak convergence of numbers. But this is a problem that's well understood in this kind of business, and I guess you wouldn't have to use experiments to get to this, but I think it's a nice example.